To derive planetary motion, we need to understand universal gravitational force, F. When objects have mass, they have a gravitational attraction to each other. So if we have a mass, m1, and another mass, m2, separated by a distance r, they will exert a force on each other. This force will be equal and opposite according to Newton's third law. So the general formula for universal gravitational force is F is equal to big G, a constant, m1, m2 over r squared. G is a gravitational constant, and it is equal to 6.67 times 10 to the negative 11th newtons meter squared over kilogram squared. Any object with a mass will have an attraction towards each other. So the sun is attracted to the earth, and the earth is attracted to the sun in equal and opposite force due to Newton's third law. At the same time, the earth is attracted to the moon, and the moon is attracted to the earth, and so forth. Second, we assume all planets travel in a uniform circular motion, so we assume centripetal force and centripetal acceleration applies, even though we know that planets have elliptical paths. We know the Earth revolves around the Sun, so there is a centripetal force keeping the Earth in its orbit. At the same time, we know that the Sun and Earth, because they both have a mass, has a gravitational attraction towards each other. So we could say the centripetal force is equal to the gravitational force. So mass of the Earth times centripetal acceleration, and it is the mass of the Earth because the Earth is being pulled into the circular motion, is equal to big G, the gravitational constant, mass of the Sun, mass of the Earth, over r squared, which is the distance from the center of the Sun to the center of the Earth. Now we could simplify. The mass of the Earth cancels out. So A equals to gravitational constant times mass of the Sun over r squared. To solve for the velocity that the planet or the satellite must maintain to keep its orbit is we must substitute in for AC. We know centripetal acceleration is also v squared, velocity squared, over the radius. So v squared over radius for AC is equal to g ms over r squared, and r on the bottom cancels out, and then we take the square root. So v is equal to square root of g ms over r. If you notice, the velocity and AC is independent of the mass of the object that is doing the orbiting. It only depends on the mass that's in the center. Formula for velocity is distance over time. Since we are traveling in a circular motion, the distance traveled is 2 pi r, or the circumference of the circle, over the period. We use the period t because it is the time to complete one cycle, I'm going to start with AC is equal to G ms over r squared. AC we stated was v squared over r, which is equal to big G ms over r squared. One of the r's cancel out in the denominator. So now I'm substituting in for velocity. Velocity is 2 pi r over t. We are going to square that. This is equal to big G ms over r. Now I'm going to square the left side, so that's 4 pi squared r squared over t squared equals to G ms over r. You're going to cross multiply. So then t becomes, or I'm going to leave it at t squared, becomes 4 pi squared r cubed divided by G m subscript s, and we need to take the square root. So t is equal to 4 pi squared r cubed over GMS. Or you could even simplify it a little bit further. You could simplify it a little further by taking out the 4 pi. So it becomes r cubed over GMS. And again here too, if you notice, it is independent of the mass of the object that is doing the orbiting. It only depends on the central object. So here's the formula for a period. Here's the formula for the velocity to maintain its orbit. Here's the formula for gravity or centripetal acceleration or gravitational field.